So this video, we're going to continue talking about the kinetic molecular theory and looking at the distribution of speeds in molecules. Just a reminder, what we know already from the kinetic molecular theory is that temperature is related to, so I'll just draw this little wiggly sign, related to the average kinetic energy. So I'm going to write Ke here for kinetic energy and put an over bar. Oftentimes as a symbol when you write an over bar, that means to take the average of the quantity underneath. Another thing that you'll sometimes see is to write the term that you want to average in these kind of alligator brackets, so greater than, less than symbols. So this also means average kinetic energy. So if you'll remember, we've talked about kinetic energy some, and the kinetic energy for a particle that's flying around is given by this formula from physics. So kinetic energy is equal to 1/2 the mass of the particle, so that would be the mass of our molecule, times its velocity squared. So you see that there's this connection here between speed, how fast a molecule is moving, and its kinetic energy. So 1/2 mv squared. So since this is the average kinetic energy, we know that that is related to temperature. But not all the molecules in our gas sample are going to be moving at exactly the same speed. So imagine that we have a gas here, right? Whoa, that's a funny shaped box over here. Anyway, so we have a gas and it's at some constant temperature T. Now what we imagine is that the little gas molecules that are in here, there's one, there's another one, there's another one. Well, they're all moving around. Now their kinetic energy, their average kinetic energy, is going to stay the same. But as molecules bump into each other, sometimes some of them will speed up and sometimes some of them will slow down. So some of them will be going very fast, ricocheting off the walls. Others will be moving more slowly until they bump into a faster moving molecule. And some will be moving in between. And so in this video, the question that we want to answer is, well, how many are moving at any given particular speed? So the kinetic molecular theory actually lets us calculate that. So we can start with those statements from our kinetic molecular theory, and then we can develop a mathematical model to figure out this speed distribution. Now we're not going to go through all the details, we're just going to be interested in the results. But before I tell you about that, I need to tell you about what we mean by a speed distribution. So let's imagine we're doing a different experiment than with gases. Let's imagine we're sitting out at a big superhighway that's around a major metropolitan area, and we've got a radar gun, and so we're clocking traffic, and we want to know how fast our car's moving. So what we do is we take our clipboard out there and our radar gun, so this is our clipboard, and we record the speeds for each car that we watch go by. So we have this list of data. Now what we're going to do is a special kind of plot. This plot is called a histogram, and you've probably seen plots like this before. So let's draw some axes in here. Okay, so in this axis what we're going to plot is speed. That's speed. So in this axis over here what we're going to do is we're going to plot the number of cars that are going at a particular speed. All right? So what we're going to make is something that looks like a bar graph. So we're going to map out a little area of speed. So all cars, traveling between, say, 40 and 43 miles an hour, we're going to count those. And so that's one bar here. And then we're going to count the number of cars going between 42 and 45. All right, so that's maybe a little bit higher bar. And we keep on doing that for all of the speeds that we've recorded. So my bar graph's looking a little funky. These bins are supposed to be equal in size. Okay, and it's sort of what you would expect. That there are many cars that are going sort of this typical speed, and there's some that are going really slow and some that are going really fast, unfortunately. So now this is called a distribution. So it tells us how many cars on the highway that we measured are going at a particular speed. So if we were to do this a whole bunch of times, we'd get pretty good idea that this data was representative of sort of how all cars travel. So if we've done this enough times, if we get enough samples, then we get an idea of the actual distribution for speeds, and we would think that that's pretty representative. So if you asked a question like, hey, on this highway, what is the most probable speed that a car is going? Well, you would say, oh, up here, this highest bar right here, more cars were going that particular speed or in that particular range than anywhere else. So that's probably the most likely speed if you had to guess. So another way that we can write this over here, this axis label, instead of counting the number of cars, we can simply write it as a fraction. So we can divide by the total number of cars and write it as a fraction, or as a percentage if we were to multiply by 100. So oftentimes, instead of writing number of cars, we will simply write fraction. And so if this bar up here were at 0.3, then that would tell us that 30% of the cars were going at a speed in this range. Now that's actually pretty big given the rest of my distribution here. But this little histogram then gives us what we call a distribution. And it's related then to the probability that any particular car is going any particular speed. So you can ask, oh, what's the chance that a car is going, 95 miles an hour? Well, that would be way out here perhaps. And then we could look over and figure out the fraction of cars that were going that speed. And we could say, hey, that's probably the likely percentage of cars that are going that speed. So 5% or 2% or whatever it happens to be. So there's this connection then between a histogram plot and a probability. So if we were to make these bends really, really narrow, so like half a mile an hour in between these things, and we still had a lot of data, then instead of drawing this little boxy plot, we could sort of connect the tops of the boxes through with sort of a smooth curve, kind of like this, right? And so this would be what we call a continuous distribution rather than a bar graph, but it would show the same kind of information. So the peak right here would be our most probable value. So most probable, that means most likely, and then you see that they're less likely on either sides, and any particular value you could work those out. All right, so this is an example of the speed distribution for cars. And so what we're going to be interested in is looking at the speed distribution for molecules in a gas. So let's scroll down and look at what that might look like. So in a gas, then, we can start with our kinetic molecular theory model, and then use physics to tell us at any given temperature how many molecules are moving at a given speed. So this is sort of a prediction then from our theory. And if we plot the fraction of molecules over here, so I'll just abbreviate that frac, F-R-A-C-T, fract of particles. And so these will be fractions like 0.2, 0.1, whatever. So the fraction of the particles, that would be equivalent if it were 0.1 to 10%, if it were 0.2 to 20%. It turns out that when we do this calculation, that for a gas, oops, let me label my other axis here. Forgot to do that. This is going to be speed down here. And a good unit for speed, SI units, would be meters per second. Okay, so what does this graph look like using the kinetic molecular theory? Well, the graph looks like this. So there's a steep peak, and then it falls off sort of more slowly, like this. Now, I exaggerated that a little bit. It's a little bit more symmetric than this, but this is kind of the general shape. So again, this value right here, this is our peak. So I'm going to draw a dashed line right there. That's our most probable speed. Now in our textbook we use U for speed a lot, so I'm going to use that instead of V. So this is U sub MP, so the subscript is M and P, which stands for most probable. So that's going to be the most probable speed for our gas. And so again, like with cars, you see that there are a few molecules that are moving really slowly. Most of them are moving at this sort of peak speed, and then there are some that are moving quite faster than that. And so there's a little bit of asymmetry here in the distribution. So this side, we've got a little more molecules moving at higher speeds than down here at lower speeds. All right, so this is typical of what gases predict, and this is a theoretical prediction. So before the kinetic molecular theory, we didn't know that this was what it would look like, but this is what the model says. So how do we know that our model's right? Well, we need to go out and do an experiment where we're actually trying to clock the speeds of molecules. Now, that's a pretty hard experiment to do, and I won't go into the details, but just believe me that it can be done. There's a really special technique. If you're curious, you can ask me about it, and I'll be happy to tell you. So using that experiment, we can get data, and it turns out that the data matches the theory curve very, very well. So these two align very, very well, as long as you're under conditions where the ideal gas law holds. So when you've got relatively high temperatures, around room temperature or above, or relatively low pressures, around 1 atmosphere, 2 atmospheres, or below, then the data is going to fit this curve really pretty well. So that's the distribution of speeds. Okay, so now let's think about what happens. Well, actually, let's write down some equations for this. So we'll write down some equations for this. So we might be interested in several different quantities. So I've labeled UMP here. Another common quantity that we're interested in is in something called the RMS speed. So I'm going to write URMS over here. And I'll tell you what RMS stands for. RMS stands for root mean square. And that's what you get if you take the speed U and you square it, and you average it. So I'm going to put that in these sort of triangle brackets. So we're averaging the squared speed. So see what we're doing down here? RMS. First you square, then you average. Mean means the same thing as average. And then we're going to take the square root of that. So that's what we mean by RMS speed. So where does this come from? Well, it turns out that the average speed shows up in our kinetic energy formula. Kinetic energy equals 1/2 mu squared. So that u squared is there. So if we average the kinetic energy, what we're going to get out is something that's related to the average speed. Then we take the square root of that. And this gives us kind of an idea of what a typical speed is in the molecule. So this is one way of talking about kind of an average speed. And on this graph, because of the asymmetry, if there were symmetry in this graph, then the most probable and RMS speed would be on top of each other, but the RMS speed turns out to be a little bit higher than that. So I'm going to draw, and this is exaggerated a little bit, another dashed line out here, and this position over here of this dashed line is URMS. Now from the kinetic molecular theory of gases, we can actually write an equation that lets us calculate URMS based on other parameters that we know from the gas law. And it turns out to be this. It's the square root of 3, that's the number 3, R, that's the gas constant R, T, that's the temperature in kelvins, divided by capital M. And capital M is going to be our symbol for molecular weight or molar mass. So that quantity. All right, so this tells us, as we expected, that average speed is related in some way to temperature. So we see that as temperature goes up, speed is also going to go up. But it's not a direct relationship, right? So if we double the temperature, the speed is going to only go up as the square root of 2. So if we replace t with 2 times t, then the speed is going to be the square root of 2 times faster, this RMS speed. So you may be interested in knowing where these other terms, the most probable speed and an average speed, come from. So let's write those down as well. So here are 2 more formulas. So U average. So this is the average speed calculated in the way that you know how to calculate an average. So U average, it turns out, is equal to the square root of 8 RT. So that's the number 8, RT, divided by pi, that's 3.14, that pi, times the molecular weight again. All right, so there's another equation for the average. Where does this average occur on our graph up here? It actually turns out that the average is going to be a little bit less than the RMS speed. So they're both measures of a typical speed in the gas. Boy, look at that wobbly dash line. I'm sorry about that, folks. Anyway, but this speed right there is our average speed. And the average speed is going to be a little bit lower than the RMS speed. And here's the formula that we could use to calculate it. Finally, we'll write down a formula for U most probable. And again, this comes from solving the equations in the kinetic molecular theory. So U most probable is going to be the square root of 2 RT over M. The capital M and the R and the T mean the same thing that they did before. So these are 3 equations that we can use to calculate what it would mean to be a typical value for a speed. So it's interesting, if you do one of these calculations, say for nitrogen, then you're going to come out with a speed that's very close to the speed of sound. And that's because air is nitrogen molecules mostly, and so the reason that sound propagates at the speed that it does is because that's as fast as molecules can travel on average in a gas at a particular temperature. So that gives us our speed of sound. So molecules are really ripping around. They are moving quite fast at the speed of sound, rocking around inside those little boxes and inside our containers and bouncing against us at that speed all the time. So it's pretty impressive. Now let's look at one other feature. So we've looked at these 3 equations and how they connect to this curve, right? We've talked a little bit about how temperature can change each of these sort of measures of a typical speed in a gas, because that's kind of what our interesting question was. What is a typical speed in a gas? So now we have equations to calculate that. Now let's think about what happens both as we change temperature and as we change molecular weight to the shape of this curve. So that's where we're going to go next. So let's clear off some space to work in. So now we're going to look at some different plots. So I'm going to sketch my axis back here. So this is speed again down here in meters per second, and this is the fraction of molecules. So this is my speed distribution plot. Okay, so let's imagine that this is at temperature T1. Now, how is the distribution going to change if we pick a hotter temperature at temperature T2? And we want to choose T2 so that it is greater than temperature T1. So now we've got a hot gas. So how are things going to look different? Well, what we know is that molecules are going to move faster because we're at a higher temperature. And in fact, that happens everywhere along this curve. So the curve basically gets squashed and shifted out this direction. So it gets kind of squashed down and shifted out towards higher speeds. So now we've got more molecules that are moving at higher speeds. So at this particular speed right here, we've got a higher number of molecules in the red curve than in the white curve going at that speed. So the fraction is higher. So we've pushed everything out this direction. So this is the curve at temperature T2. And so that's typically what's going to happen as you increase the temperature. You're just going to squash this curve and flatten it out and shift it further and further out in speed so that we're having molecules traveling at ever increasing speeds. Now let's think about what happens with molecular weight. So we've seen that average speed from our equations goes as 1 over the square root of the molecular weight. So we're going to sketch out another axis, another set of axes here. So again, speed and fraction of molecules. To save time, I'll just write that as fract. Now let's look at two different speed distributions for two different molecules. Okay, let's say that this is the curve for O2 gas. And now we want to look at a different curve for a different molecule. Let's look at helium. Now we also want to look at helium gas. So what might the curve for helium look like, assuming that we're at the same temperature for both the oxygen and the helium? So what we know about both of these guys is that at the same temperature, they're going to have the same average kinetic energy. So that's an important enough thing, I'm going to write it down. Because we're at the same temperature, the kinetic molecular theory says these two gases are going to have the same average kinetic energy. Remember those little angle brackets, they mean average the thing inside. So since we have the same temperature, it must be the case that these guys will have the same average kinetic energy. But remember, kinetic energy of a particle is 1/2 mv squared. And so the average kinetic energy is going to be 1/2 the average speed squared. So let me just write that down too. Average kinetic energy is equal to 1/2. Now, they all have the same mass, so that doesn't have to be averaged, but they have different speeds. 1/2 u squared averaged. So that's how we would calculate the average kinetic energy. Okay, so if these two gases have the same kinetic energy, well, they're going to have different average speeds because they have different masses. And since the mass of helium is so much lighter than the mass of oxygen, off the periodic table we can see that, we know that those helium atoms are going to have to be moving faster. So its curve is going to look like we saw for the one at higher temperatures, squashed out here to higher speeds. So this is helium here, which has a lower molecular weight. So at the same temperature, the species with lower molecular weight, speedier, they're zipping right around. So you can think of these higher molecular weight oxygens. They're big and heavy, so they kind of lumber around really slowly, boom, boom, boom. Whereas the fast-moving heliums are really zippy, bzz, bzz, bzz. So they're moving around at this high speed. It's important to have the sound effects, by the way. Anyway, so that's how we can tell the difference in speed distributions between two gases that have different molecular weights. And the differences in speeds goes as 1 over the molecular weight, as we saw in our equations before. So that's a little bit about speed distributions that we can predict from the kinetic molecular theory of gases.